Hello, everyone. Welcome. Thank you for joining today. We're here today to talk about connected product development, specifically as it relates to connected microcontroller-based devices and our product called Amazon FreeArt. So again, I'm Rob Cochran, a senior product manager at AWS IoT, and I'm here with Dan Griffin, who's one of our senior engineers in AWS IoT as well. So before we dive into some of the details, I just want to set a little bit of context for the discussion today. AWS IoT launched a little over 2 years ago, and that consisted of AWS IoT Core, which is a secure device connectivity and messaging platform. Since then, we've launched AWS Greengrass, which is our edge compute solution. We've also added several features in the cloud, including fleet onboarding and management, software updates. And that falls under the umbrella of AWS IoT device management. We've announced AWS IoT Device Defender, which is a fleet audit and protection mechanism, and then AWS IoT Analytics, which is IoT analytics, data processing, and a few other tools. We also offer a service called AWS IoT One-Click, which is kind of an end-to-end service for simple devices. But again, today what I want to talk about is connected microcontroller development and specifically Amazon FreeArt. But before we really get into the details, I think it makes sense to start with something that we can all agree on, that this picture, it doesn't show a cake. It shows many of the ingredients you might use to make a cake, and maybe you have an idea of what sort of cake you'd like to make. I'm sure you know people who'd be happy to eat it, but there's work to be done. So if we apply the same logic to this picture, this is not a connected door lock. Again, it has many of the components you might use to build a connected door lock. And you might have an idea of various market segments that you'd like to sell this door lock into. But there is work to be done. And when the industry talks about tens of billions of connected devices, the vast majority of those are going to be microcontroller-based. But what it assumes is that connecting those devices will be easy. And today it's not. And so we took a look at this challenge and said, what are some of the common challenges we see in embedded development specifically related to microcontrollers? And so the first is really speed to market. And what we see today is that many companies spend a lot of time just getting connectivity working, and then even more time getting it working reliably and securely. And so these things slow down development, lead to long test and iteration cycles. It means it's more expensive to introduce a new product to market. We also have several customers who have not just one product, but several products and several product generations. And this matrix leads to a lot of complexity in managing not just the software, but the supply chain of components that go into embedded devices. And we know that companies want to run on a broad variety of hardware. We work to abstract away some of the complexity of embedded development. And the last piece is cost. To address both the speed and complexity challenges, many companies today license what can be expensive software to get some of the underlying components for connectivity and security working. And so this, again, adds cost to microcontroller-based development, which is a critical factor in a successful IoT product. So just about 2 months ago, we launched Amazon FreeArt, which is an IoT operating system for microcontrollers. And it's really specifically targeted at addressing the challenges that I just spoke about, creating a faster time to market, minimizing complexity, and reducing cost. And we did this by starting with the #1 real-time operating system for microcontrollers called FreeArt. So we took that FreeArt kernel and then we extended it with device software for connectivity, security, and over-the-air updates. We then developed a set of integrated cloud services that facilitate the use of our device software. And we did this all with a broad ecosystem of hardware and tools partners so that you can use Amazon FreeArt in your chosen environment. So who's this for? Now, The example we'll talk about a little bit later, and when Dan gets into his demo, we'll talk about is the example of oil pressure sensors on an oil rig. But Amazon FreeRTOS is broadly applicable to any microcontroller-based embedded devices. So we've engaged with customers for smart meters and fitness trackers, washing machines, robotics, automotive, smart home, door locks, and I'll tell you about some of our customers in that space, medical devices, HVAC systems, and consumer electronics. So to make that a little bit more tangible, I want to talk about a few of our early customers who have built prototypes using Amazon FreeRTOS. Chalet was one of the first engaged with Amazon FreeRTOS, and they build physical security systems, specifically door locks. And they took Amazon FreeRTOS and built it in to their next generation connected door lock, and were able to get it up and running in just under a month. Hive has built a suite of smart home products, and with Amazon FreeRTOS, built a water leak detector. Honeywell built a connected thermostat and control system, and NASA's Jet Propulsion Lab built a robot running Amazon FreeRTOS, connected to a larger robot running AWS Greengrass, and all synced with the cloud via AWS IoT Core. And if you're interested, you can see that demo online as well. So I want to dive a little bit into the ways in which we're addressing these specific challenges and talk about some of the features that Amazon FreeRTOS offers. Again, we started with a well-established foundation. The FreeRTOS kernel is the #1 real-time operating system for microcontrollers and has been in the market for 14 years. It's already used on billions of devices in production. And with over 40 supported architectures, it's applicable to a really broad range of microcontrollers. So this open source project is now maintained by Amazon. And when we announced Amazon FreeRTOS, we also introduced a new version of the FreeRTOS kernel, version 10. And this does two really important things. The first is a transition to an MIT open source license from the modified GPL v2 that it was previously distributed under. And this has been a long time request of many of the FreeRTOS kernel customers, and I think will be a really important change for many enterprises who are looking to use the FreeRTOS kernel in their projects. We also introduced new features that improved inter-process communication, such as stream buffers and message buffers. This is all now freely available, open source, and extensible with libraries for cloud and edge connectivity. So I'll talk about a little bit about how we extended the FreeRTOS kernel. We added connectivity specifically to AWS IoT Core and much of the functionality offered there, such as device shadows. We also offer the ability to connect locally to AWS Greengrass or other gateway. And we built this all on a bed of AWS-grade security, including TLS for a secure connection, key management on the device, and code signing for over-the-air updates. For AWS IoT Core, again, we built in much of the functionality that service offers in the cloud. So you can get started with MQTT pub/sub-based messaging. We also support device shadows, which is a digital representation of your device in the cloud. We integrate with AWS IoT Device Management, which is a new service that allows you to do things like send notifications to your devices. And we have demos that expose all this functionality in a clear way, so you can get started very quickly. And we do this basically, this integration with AWS IoT Core uses all its functionality, and it has the same pay-as-you-go pricing that any other user of AWS IoT Core has. AWS Greengrass is our solution for edge compute. I want to talk a little bit about the demo that Dan will give in a little while as a way to set context for how AWS Greengrass and how Amazon FreeRTOS can be used together. So let's imagine you're on an oil rig and you've deployed pressure sensors to the bottom of the ocean floor or to various pipes and fittings around the rig. And you want to monitor all these oil pressure sensors in real time. Now you could connect those all to the cloud, but you might have intermittent connectivity. You also might have 1,000 sensors connected sending data at some regular interval, maybe once a second. And that amount of data just doesn't make practical sense to send all to the cloud all the time. And even if you downsample it, you want to be able to run some logic to know what's happening with that data and only send the important notifications to the cloud. So with AWS Greengrass, you can run Lambda functions locally that get triggered based on certain events. So if pressure from a certain sensor or a certain number of sensors goes over a certain value, you can immediately send a notification to the cloud. So Greengrass offers this functionality today, and what we've introduced with Amazon FreeArt is the ability to easily connect to a Greengrass core using a process we call Greengrass discovery. Once you've discovered and connected to a Greengrass core, which Dan will show later, then you can do all sorts of local messaging and integrate with Lambda functions that operate at the edge. Now, again, we built this all on a foundation of security. AWS IoT Core has certain security requirements in terms of interacting with the cloud. So we built secure sockets using TLS. We also have certificate-based authentication that allows you to authenticate either with the cloud or with a Greengrass core. And we've also built a standards-based interface for key management, specifically PKCS 11. Lastly, we offer code signing that allows you to verify the code that's running on your device when doing over-the-air updates. So this basically helps developers get started with a really secure by default implementation with no open network ports and only running trusted code. It also has a really clear modular implementation, so you can pick and choose the components that are most relevant to your use case. So in addition to device software, we also built a set of integrated cloud services that facilitate the use of Amazon FreeArt. We've launched over-the-air updates, and that feature is in beta. And we also have an Amazon FreeArt console where you can configure your download of Amazon FreeArt software. So to start with over-the-air updates, this is a feature that integrates directly with AWS IoT device management. So you can select a group of devices that you want to update. You can upload a new firmware image that applies to a certain set of devices. Say you were updating the pressure sensors on this oil rig. You develop some new software, you upload it to the cloud. You can now sign that firmware image with the certificate you control. We can then enable the streaming of updates to your device over MQTT, which means you only need a single TLS connection to the cloud. On the device, we have an agent that can help validate the signature and APIs to control installation and reboot logic locally. So this makes a really simple workflow for delivering over-the-air updates to devices and an implementation that we think helps out a lot in terms of implementing security out of the gate. So the fastest way you can get started with Amazon FreeArt is configuring a download, and Dan will show how this workflow works a little bit later in the talk. But basically, this is where you can come and select not just the piece of hardware you're using, but the libraries that are relevant to your use case. For example, if you're choosing to connect to AWS IoT Core or to Greengrass locally, you can select the libraries that are relevant to your use case, and only those will be compiled into the image that you flash to the device. So to piece this all together, our philosophy in driving a faster time to market really was around creating a clean abstraction layer for developers to build applications on top of. Now, if you're more familiar with a Linux world or a cloud development world, this sort of abstraction is kind of par for the course. You expect this type of abstraction in the applications you build. If you're more familiar with microcontrollers, that sort of abstraction simply doesn't exist today. And so what we've done is tried to create simple interfaces with a modular implementation that allows you to pick and choose the functionality you want without having to drill down to the various layers below that to get everything up and running. So again, many of our customers don't want to just develop one IoT device, but they want to develop many. In fact, they might have many different product lines and several product generations that they need to manage through those life cycles. And this means they need to work with a variety of hardware, a variety of tool chains, a variety of IDEs. And so when we built Amazon FreeArt, we did it with a broad ecosystem of hardware and tools partners. With Microchip and NXP, ST Micro, and Texas Instruments, we qualified hardware and created a program so that we can more scalably introduce hardware to our customers and allow our customers to run this on a variety of run Amazon FreeArt on a variety of chips. We also worked with ecosystem and tools partners who facilitate the use of Amazon FreeArt. ARM developed architectures for microcontrollers that allows Amazon FreeArt to run seamlessly across a variety of processors. IAR Systems has a professional development IDE that makes it easy to use Amazon FreeArt in your chosen context. Percepio provides debugging and trace analysis tools, and Wittenstein offers commercial licenses of FreeRTOS called OpenRTOS and safety critical licenses called SafeRTOS. And so while bringing products to market faster and reducing complexity also helps to reduce cost, we know that in IoT devices, specifically microcontroller-based devices, cost is critical. And so we took what we knew had made the FreeRTOS kernel successful for so long and tried to duplicate some of that for Amazon FreeRTOS. So everything we've developed is free, open source, and introduced under the MIT license, and comes with no commitments to use AWS. So while we've built libraries that facilitate connectivity to AWS IoT Core and AWS Greengrass, there's no commitment to actually use those libraries if it doesn't suit your use case. So I think the best way to show what we've built with Amazon FreeRTOS is to show a demo. Again, I want to talk about the example of oil sensors on an oil rig as a way to piece together Amazon FreeRTOS, AWS Greengrass, and AWS IoT Core. So if you've deployed sensors on an oil rig, you may want those to connect locally so you can run some logic on the data coming off of those sensors. If you detect certain events, like high pressure sensor on one or many of your sensors, you will want to send a notification to the drilling engineer so that they can respond quickly to those events. So we've used Amazon SNS so that you can actually just send a text message right away to an individual via Greengrass connecting up to the cloud. So Dan Griffin will go through this example now and show you some of the technical details behind how to implement it.
Thank you, Rob. Hi, guys. My name is Dan Griffin. I'm a senior software engineer on the AWS IoT team working on Amazon FreeRTOS. My background is in software security. To run the demos that Rob has referred to, including both the Hello World demo for getting started, as well as for the Greengrass connectivity demo that I'll show you in a minute, please take a look at the Getting Started with Amazon FreeRTOS page that I'm showing here in my web browser. I'm not going to describe in detail all of the prerequisites, but I will summarize the steps that you need to do in order to get up and running, all of which are described in detail on these web pages. The first set of steps here on the main Getting Started page start with first configuring the permissions on your Amazon FreeRTOS console, as well as the user that you're using to log in to the AWS console to make it so that when you create software configurations using the Amazon FreeRTOS configuration wizard, that the console actually has permission to save those configurations to your user account. And so that's why we have this granting FreeRTOS permission step first. The next step after that is summarizing the developer boards that we support. I'm going to demonstrate using the simulator, which I'll show that page in just a minute. And then the next, of course, very important prerequisite here is that you create an AWS IoT thing, which is the backend representation of your IoT device. And in particular, we need a client credential for your device. Rob talked about the importance that we place on mutual authentication, both from the device perspective as well as from the AWS server perspective. And then in addition to that credential, you also need to configure the endpoint information and the name of your device in the code. I will show that in just a minute. Since we know we're going to use the simulator, I will then direct you to the Getting Started with the FreeRTOS Windows Simulator page. And again, I'm going to summarize these steps, but I'm not going to show all of them in detail. The first step here is to install WinPCAP. This is an open source library that our simulator uses for injecting Internet Protocol packets fully formed into the Windows kernel. And we do that because otherwise you get into trouble with most Ethernet drivers in Windows that won't let you just do raw packets. Unfortunately, what we encounter is a slight inconvenience with that approach, which is that typically you require a wired connection. The simulator usually has problems with Wi-Fi connections due to security, important security limitations of the Windows Wi-Fi driver model. Of course, if you're using one of our embedded developer boards, there's no such limitation, and whatever transports are supported by the board will work just fine, including Wi-Fi. The next step is to install Microsoft Visual Studio. The latest version is what we recommend. Provided that you're working on an open source project, you can use the community edition. Otherwise, you should use the Pro edition. Rob mentioned our configuration wizard online, and that's the next step described in this Getting Started page here. And at that point, I actually am going to transition over to the AWS Management Console and demonstrate this part of the procedure in a little bit more detail. You can see that I'm logged into the console using my internal Amazon account. I'm going to click on the AWS IoT link, which of course I visit quite frequently. This is the main AWS IoT landing page that I'm showing in my browser screen now. I'm going to click down here in the bottom left on the software tab. Over here in the center, you see Amazon FreeRTOS device software. I'm going to click on Configure Download. I know that ultimately what I want to do here in this demo is show connecting to AWS Greengrass using the Windows simulator. And you can see that that option is kind of in the middle of the list here. I'm going to click on the download link. And I'm prompted to open or save that file. I'm just going to go ahead and directly open that zip file. And what I actually want to do to make things easy for myself is I want to copy that zip folder into a separate directory so that all the files are then accessible to the IDE. So I'm going to wait for that to uncompress. Good deal. Now I'm going to drill into that folder, Demos, PC, Windows, Visual Studio. You can see here the Visual Studio solution files are .sln. I'm going to open that SLN file by double-clicking on it. That's going to open up a Visual Studio 2017 instance for me. And I do get prompted, since this is a download from the internet, I'm getting prompted, do I trust the source of these files? Yes, I do trust. So now that we've got the solution open, what I want to show you is, again, summarizing some of the prerequisites but these are the main hurdles that you're likely to encounter. And I want to give you some sense of how to get started really quickly with the Amazon FreeRTOS simulator by looking at some of the specific files in the source code that you'll have to configure in order to get started. In this include directory under application code common demos, going again back to the client credential that's required in order to authenticate using TLS to the AWS IoT MQTT broker. There are two components to that client credential. One is the PEM encoded client certificate, which I am highlighting here, that line in this file. And the other is the PEM encoded private key. What I have for my own convenience is a previous instance of this same solution that I downloaded and configured. And I will switch to the file here that we were just looking at, which is this AWS client credential keys file. And you can see this is a PEM encoded client certificate. And in this case, I'm using an elliptic curve client key, which is a capability that we support. And there are further instructions in detail of if you want to use an ECDSA key on our Getting Started guide. I will switch back to the solution copy that we just downloaded. Open up Solution Explorer again. The next file that you want to look at is this AWS client credential header. And two things important here that you'll need to do to get started for any of the demos. First, you need to configure the MQTT broker endpoint that's unique to your AWS account. And second, about 5 lines down farther, you see the IoT thing name. And this name needs to correspond to the name that you specify when you create your AWS IoT thing in the prerequisite steps. Again, I will switch now to the other browser window that I have open, the other IDE window that I have open, where I have previously configured those two settings. Here's my unique endpoint in our US West 2 region, and I've called my IoT thing name by my initials plus ECC to remind myself that I'm using an elliptic curve client key in this case. The final thing that you want to configure typically in order to be up and running with the simulator in particular is if you open up this file, freeRTOSconfig.h, and generally what I do is I just search for the word interface, and that will drop me down to this line here, which in the current version is line 164. This is very important because we're using that WinPCAP network proxy library for Windows. You need to tell, the simulator needs to tell WinPCAP which network interface to use. And as I mentioned before, that will generally have to be a wired Ethernet interface. And as well, consider that your interface, in order to connect to the cloud, will be the one that has internet connectivity, DNS and all that kind of thing. So now that I have, in this previously configured solution, all my settings from the cloud, there's one last thing I want to show you before we actually run the code. I downloaded a solution from the configuration wizard that's specifically for doing Greengrass discovery to show you how Greengrass discovery works. However, I personally recommend before you try any of the demos other than MQTT Echo, which is the Hello World demo that Rob mentioned in the slides, I do recommend that whenever you've changed your configuration, either on the back end or on the device, you run this Echo demo first, just because the Echo demo is the easiest one to debug, and all the other demos build on top of it. So now that I've got the MQTT demo uncommented and the Greengrass demo commented, I'm going to build my code, and I'm going to run the solution in the IDE debugger. And what I want to show you is in the console output, which is because I'm on a fast connection here using the simulator, the console output goes kind of fast. But anyway, the summary is that I'm seeing exactly what I want to see to know that my demo is configured correctly, to know that my simulator and my IoT thing are configured correctly. And namely what that is that our Echo demo sends 11 loops of publishing a hello world message, receiving that hello world message via a subscription to itself, essentially, from the broker, and then acknowledging each of those messages back to the cloud and then back to itself. And we use that kind of back and forth ping pong loop to really know that, okay, subscribe is working, publish is working, and then we run the loop 11 times just as kind of a, that seems like just enough. Anyway, I'm not going to let it run all 11 times at this point. Instead, what I'm going to do is I'm going to stop the demo since I'm confident now that I can move on to the more complex examples. And what I'm now going to do is I'm going to comment out the MQTT echo demo, again, in this file, demorunner.c. And I'm going to uncomment the Greengrass discovery demo. And I'm going to save that. I'm going to build. Nice, fast, incremental build. Before I run the demo, I want to point out that there is lots of documentation about getting started with Greengrass, which is now one of the dependencies that I'm going to use when I run the Greengrass connectivity demo. And I draw your attention to back in the Amazon FreeArt user guide online. If you scroll down a bit in the table of contents on the left, you'll see this next steps heading. And if I click on next steps, looks like the fourth item down is Greengrass discovery demo. And in the Greengrass discovery demo page, the very first link is getting started with AWS Greengrass. And that page describes in detail how to set up a Greengrass core and make it accessible to your device, which in this case, I need a Greengrass core that's on the internet, that's accessible to the simulator because the simulator is relying on an internet connection in order to do back and forth. Of course, a primary scenario for Greengrass is to service devices that don't have an internet connection. So I want to be clear that this is not required. This just happens to be a convenient demo configuration. I'll now switch back to the IDE, and I've built my solution to run the Greengrass discovery task here in AWS demorunner.c. So again, I'm going to run the solution in the debugger. And let me summarize what's going to happen in the console output of the Greengrass discovery demo. What we're looking for is a few things to happen here in the background. The first step is, because I am showing an internet-based scenario, I'm going to take advantage of the Greengrass discovery feature offered by AWS IoT, which is for the device to do an HTTPS GET to the cloud and receive a list of Greengrass cores that are available to it. And what the device code then can do is run through each of those cores and try to connect to them. And those can be either IP addresses or DNS names. And what I see, for example, in line 15 of my console output that I just highlighted is that the Greengrass device has been discovered, which is good news. In line 23, I see that the device next took that discovery information, that DNS name in my case, connected to the MQTT broker on MQTT. And then further down, I see that the device published several messages to the Greengrass core to its MQTT broker. Now, in this demo, I've actually taken a couple of steps further than just the default demo we have for Greengrass discovery. And let me explain what those steps are. Rob mentioned this example of, let's say you're on an oil rig and you've got some pressure sensors, and typical scenario for AWS IoT is that those sensors are not internet accessible. Of course, your rig is likely to be on a satellite connection, highly latent connection, intermittent. It's not sensible that if you need to be able to, for example, take immediate action, you don't want to have to wait for a round trip time to the cloud. Well, this is exactly that scenario. What's happening is that when the device detects an out-of-range reading, it's actually calling a Lambda that I've configured in the cloud, but that gets seamlessly synchronized to my Greengrass core whenever the Greengrass core happens to be connected, have available connectivity to the cloud. And what that Lambda function does in turn is it triggers an AWS Simple Notification Service event. And what that SNS event does is it sends me a text message to my cell phone. Of course, unfortunately, since we don't have a camera, you can't see the text messages that just rolled into my cell phone. But suffice to say, for each of the 3 test messages that were sent by the Greengrass demo, via that chain, up through Greengrass Core, through Lambda, through SNS, I received those text messages on my phone. So in summary, I want to point out that in order to learn more about Lambda and SNS, I encourage you to take a look at the main AWS Getting Started Resource Center, a webpage which I'm now showing on my browser screen here. And I also want to point out that the power of the model for Amazon FreeRTOS and Greengrass Core is that from the Amazon FreeRTOS device perspective, the Greengrass Core looks and behaves exactly the same as the cloud itself. So the programming model is exactly the same. You don't have to change any of your application code to switch between the cloud and just local connectivity only scenarios.
Thanks, Dan, for the demo. So just to wrap up, I'd like to kind of give a call to action here, how you can get started. So there's several places you can find Amazon FreeRTOS. The first and kind of recommended channel is through the Amazon FreeRTOS console, which Dan showed you a little earlier on. All of our code is also available on GitHub under FreeRTOS. FreeRTOS.org was and will remain the home of the FreeRTOS kernel. And you'll also be able to find the FreeRTOS kernel on SourceForge. Thank you very much for your time. Appreciate you taking some time out of your day. Please visit us at aws.amazon.com/freertos. You can also follow us on Twitter at real_freertos for news and updates.